Yeah, thanks, Xinji, and thanks everyone for the good presentation. I think we can move to our second paper presentation session. There will be 4 papers. First one is characterizing the adversarial vulnerability of speech self-supervised learning from Haibing Wu and the rest of the authors. The second paper will be membership inference attacks against self-supervised speech models from Wei Chen Zhen and our authors. And the third one will be pretext task selection for multitask self-supervised speech representation learning from Salah Salim and the rest of authors. And the fourth one will be the race, decorating latent space for low resource audio representation learning from Shreyan Ghosh and the rest of authors. I think we can start from the first paper if Haibing or the authors are ready, and please share your screen and presentation.
Okay, I'm ready. Can you see my PowerPoint?
Yes.
Okay, great. Hello, I'm Haibing Wu. Today I will present my paper characterizing the adversarial vulnerability of speech self-supervised learning. This is today's outline. Today's presentation is divided into 5 parts: motivation, background, proposed methods, experiment, and conclusion. For the motivation, this paper's idea is based on a leaderboard named Superb, and this leaderboard aims at benchmarking the performance of speech self-supervised learning models, and it shows that speech self-supervised learning models greatly improve the performance of downstream tasks. However, the adversarial robustness of such paradigm haven't been investigated. So in this paper, we do some very early study to investigate the adversarial vulnerability of such paradigm. Then let's get into the backgrounds. I will talk about what is adversarial attack. In this figure, we have a well-trained image classification model. Given a picture of cat, the model will predict cat with a very high confidence. However, the attackers can find some small noise called adversarial noise and add it to the original image to generate the adversarial sample. The attacked image is very similar to the original image, but the network will predict something else, and using such adversarial noise to generate adversarial samples to attack the machine learning model is called adversarial attack. Then I will briefly talk about the super benchmark. The paradigm is showing in this figure. The speech self-supervised learning models play the role of upstream models. The upstream models learn some general usage knowledge from a large amount of unlabeled data. The features are then extracted from the upstream for downstream tasks. Following the super paradigm, given the audio inputs, here we use X, it will go through the pre-processing procedure, and then the pre-processed data X prime will be fed into the upstream model to get H1 to Hn. Then these hidden features are followed by the layer-wise weighted sum procedure to get the final embedding Z. The final embedding will be used for the downstream model training and inference. And in this paper, we use 2 models, namely Hilbert and Wave Vector, to generate adversarial attacks. And the main reason we choose them is that in the setting of Superb, the 2 models both get excellent performance in all the downstream tasks. Let's get into the attack methods. Note that the adversarial attack are conducted only in the inference time. The main idea is that once we can destroy the embeddings, here denoted as C, extracted by the upstream model, the destroyed embeddings will let the downstream model give wrong answer, fulfilling the attack target. So here Z is our target to destroy. Then let's talk about how to find the adversarial noise. Actually, the word destroy here means that we want to maximize the difference between the genuine embedding and the adversarial embedding. Here we use ZA to denote the genuine embedding and the ZA tilde to denote the adversarial embedding. But at the same time, we want the genuine audio X and the adversarial audio X tilde as similar as possible. So in order to fulfill these two objectives, we introduce the basic iterative method to do attack. This method is shown in this equation, where delta is our objective, the adversarial noise. The L2 norm of ZA minus ZA tilde is the objective function to derive the gradient. Alpha is the step size. Sign is the function which gets the sign of the gradient, and n is the iteration number. And here the clip function is a norm constraint which conducts element-wise clipping to make sure the original sample X and the adversarial sample X are as similar as possible. Based on the based on the knowledge accessed by the attacker, we divide the attacking scenario into zero knowledge attackers and the limited knowledge attackers. The difference between them is that whether they know the target model, the detail of the target model. Then we go to the experiments. For the setting of our experiments, we randomly select 100 genuine samples for attack and repeat the experiments 3 times. Then we get the mean and the variance of the attack performance. Also, we introduce the Gaussian noise with the same noise to signal ratio for comparison as the baseline. This is the experimental results. Note that the direction of the arrow in the second row denotes the direction towards the better performance of the downstream task. For example, downward arrow for ASR means that the lower the word arrow rates, the better the ASR performance. So for attacks, because we want the model perform worse, the higher the word arrow rates implies the more powerful attack. The first column denotes the method to generate the adversarial samples versus the target model. For example, wave to vector dash wave to vector denotes that the proxy model for generating adversarial sample is wave to vector 2, and the target model is also the wave to vector 2. And the row A and the row G are the limited knowledge attack scenario. Row B and the row F are the zero knowledge attack scenarios. And the row C and the row G denotes using the samples perturbed by Gaussian noise. Row D and the row H denotes the clean sample, the performance of the clean sample. From A and E, we can see that limited knowledge attackers achieve effective attack performance for all downstream tasks. And from C and G, we can observe simply adding Gaussian noise cannot degrade a well-trained system for the attack purpose. And from row B and F, we can see zero knowledge attackers achieve relatively weak attack performance, but the attack performance is better than the Gaussian noise. Let's get into the conclusion. In this paper, we do some early study to expose the vulnerability of the superb paradigm to adversarial attacks. And for the future work, we will investigate attacks with higher transferability and less imperceptibility. And the long-term goal is to come up with adaptive defense methods that offer protection against increasingly dangerous attacks. That's all. Thank you.
Yeah, thanks, Haibing, for the presentation. If the audience have any questions, please type on the chat, and we will go through the questions at the end of the session. The next speaker will invite Wei Chen Zhen to discuss his paper.
Could everyone see the slide?
Yeah.
Okay. Hi, I'm Zheng Weichen from National Taiwan University, and I'm going to present our work, Membership Inference Attacks Against Self-Supervised Speech Models. Recently, self-supervised learning models have become an important component of speech processing. They can generate general-purpose representations that benefit a wide variety of downstream tasks. However, despite their ubiquitous deployment, the privacy risks of these models have not been well investigated. It is inevitable for us to make sure whether there are potential privacy risks in self-supervised speech models before deploying them to products. In this paper, we study and propose a basic method of a specific type of privacy attack, which is the membership inference attack to these models. Membership inference attack focus on the privacy of the individuals whose data was used to train the model. Given a model and an exact data point, the adversary wants to know whether this data point was used to train the model or not. The motivation is closely related to the original goals of differential privacy. And this attack is often served as an counterreef of more severe privacy issues. Here we propose a membership inference attack framework against self-supervised speech models on the black box axis. Here's the proposed framework. Since self-supervised speech models are pre-trained on large-scale utterances from various speakers, we consider launching membership inference attack in two scenarios. First one is the utterance level, and the second one is the speaker level attack. We first take a look at the utterance level attack. For utterance level attack, we aim to determine whether an utterance belongs to the pre-training dataset of the target model or not. The attack falls into two stages, namely basic attack and improved attack. In basic attack, we first use the target model to encode the utterance into a sequence of frame-level representations, followed by a vector similarity metric function to calculate the similarity score between every individual pair of these frame-level representations. Then the utterance level similarity score is determined by averaging these pairwise similarity scores. Finally, we use the utterance level similarity score to decide membership. If it is above some predefined threshold, then we'll say the utterance exists in the pre-training dataset, otherwise it is not. Moreover, since using a predefined similarity metric may not achieve the best membership inference performance, we further adopt the concept of pseudo-labeling to propose an improved version of utterance level membership inference attack. In the improved attack, we first inference an auxiliary dataset which consists of unseen utterances and compute the utterance level similarity score for each of them. Then K utterances with the highest similarity score are selected and labeled as seen to the target model, while the K utterances with the lowest similarity score are also selected and labeled as unseen. These selected utterances are then used to train a deep neural network that takes the frame level representations of the utterance as input to predict the utterance level similarity score. That is to say, in the improved version of utterance level attack, we use the deep neural network to replace the predefined similarity metric function and the average operation of the basic attack. The predicted similarity score of the scene should be closer to 1, while that of the unseen should be closer to 0. Then we move on to the speaker level attack. For speaker level attack, given a set of utterances from the speaker, we aim to determine whether this speaker belongs to the pre-training data set of the target model or not. Likewise, the attack is divided into basic attack and improved attack. In basic attack, we first encode each utterance into frame level representations, followed by an average pooling layer to generate the utterance level representations. Then a similarity metric is adopted to calculate the similarity score between every individual pairs of all the utterance level representations. Then speaker level similarity score is determined by averaging these pairwise similarity scores. Again, we use the speaker level similarity score to decide whether the speaker exists in the pre-training data set or not. Moreover, for the improved version of speaker level membership inference attack, we first start with inferencing on an auxiliary data set, which consists of utterances from several unseen speakers. Then the utterances of K speakers with the highest similarity score are selected and labeled as seen to the target model, while the utterances of K speaker with the lowest similarity score are also selected and labeled as unseen. These selected utterances are used to train a deep neural network that takes a pair of utterance level representations as input to predict the pairwise similarity score. Hence, in the improved version of speaker level attack, the deep neural network is to replace the predefined similarity metric of the basic attack. In our experiment, we applied the proposed attack against 4 self-supervised speech models: Hubert, Wave2Vec2, CBC, and Terra. The library speech 100 hours served as the scene data for the target model, while the development set and the testing set from the same corpus serve as the unseen and the auxiliary data set. The predefined similarity metric in the basic attack of utterance level is 1 minus cosine similarity, since we empirically find out most utterances have relatively low similarity scores. On the other hand, the similarity metric of speaker level is simply the cosine similarity, as most speakers have similarity scores closer to 1. For the number K to train the deep neural network for the improved attack, we have K equal to 100 for utterance level and only K equal to 1 in speaker level. The performance of the attack is reported with adversarial advantage, defined as the difference between true and false positive rates. A higher advantage score implies a better performance of distinguishing the seen and the unseen. The random guesses will offer an advantage score of 0. We evaluate the membership inference attack with the predefined threshold equal to the each decile range of the similarity score of the auxiliary data set. The dashed line the dashed line are the result of the basic attack, and the solid line along with the plus denotes the result of improved attack. From the result of utterance level attack, we can see that Wave2Vec2 is already vulnerable when applying basic attack. That is to say, Wave2Vec2 is vulnerable to reveal membership information. Additionally, using a deep neural network in the improved attack significantly boosts the attack performance, where all the self-supervised model have the highest advantage score larger or equal to 0.6. Furthermore, at speaker level attack, the membership information leakage seems to be more severe than the one in the utterance level. You can see here. When applying basic attack, most of the self-supervised model have the highest adversarial advantage score larger than 0.5, except Terra. And the 2 state-of-the-art model, Hubert and Wave2Vec2, even suffer more. Moreover, we surprisingly find out that using a deep neural network in the improved attack can achieve a near optimal attack performance. The result indicates that self-supervised speech models are weak in preventing membership information leakage, regardless of the self-supervised objective. We then inspect the generalizability of the proposed attack. For simplicity, we only show the highest advantage score here. Here we use the VCDK corpus as the auxiliary data set to train the deep neural network in the improved attack. You can see that the result remains similar, which indicates that the success of the proposed attack does not result from special selection of the auxiliary data set. We also conduct an ablation study showing how the model size and the size of the pre-training data set affect the attack performance. For the model size, we compare the Hilbert and the weight to vector variant. The blue one indicates the smaller model, while the orange one indicates a larger model. The result showing that using a larger model leads to a lower speaker level attack performance here, preventing itself from speaker level membership information leakage. But when it comes to utterance level, there's no such guarantee that which model size is better. And for the size of the pre-training data set, we compare the Wave back to and the Terra variant. And also the blue one represent that the model is trained on a smaller data set. And we can observe that in both utterance and system level, pre-training the model on a smaller data set results in a lower attack performance, as you can see it here. And these counterintuitive results strongly motivate the need for an in-depth study on the influence of these factors. To sum up, in this paper, we present the first privacy analysis on self-supervised speech model using black box membership inference attack. The results show that these models are vulnerable to both speaker level and utterance level attacks to reveal sensitive membership information. And the proposed attack is robust to the choice of the auxiliary dataset. And we also conduct an ablation study on how the model size and the corpus size affect the attack performance. Thanks for listening.
Yes, thanks, Wei-Chen, for the presentation. Next, we will go to the third papers, a pretext text selection for multitask self-supervised speech and audio representation learning from Salah. Would you like to go ahead?
Hello, everybody. My name is Salah Zayem, and I'm here to present our work on pretext task selection for multitask self-supervised speech and audio representation learning. So I'll start with a quick introduction. So very quickly, in self-supervised settings, we learn speech embeddings through learning to solve pretext tasks. You can see in the green boxes above a bunch of very basic pretext tasks presented here. And those speech embeddings are in the second phase fed to a downstream training model to perform the classic tasks of interest, like ASR or speaker recognition. So I've talked about the pretext tasks. Actually, to test one selection of them, we'd have to go through the two training phases. And this involves a lot of computation. So the question in this work was how to efficiently select a group of pretext tasks in self-supervised learning settings. So the objective is the first sentence written here. And to start, we will talk about finding a function that would beforehand score the usefulness of a given pretext task towards solving a final downstream one. So I introduce our conditional independence-based estimator. The main idea is pretty simple. If the speech samples we're considering are independent of the pretext task labels, given the downstream labels, conditionally on the downstream labels, then these pretext tasks should be good. This is inspired from theoretical work done by the team of Jason Lee and collaborators. So I'm talking here about pretext task labels. We could also call them pseudo labels. I'd have to say here that in this work, we are restraining ourselves to tasks that consist in predicting an automatically generated label. So I talk about pseudo labels or pretext tasks labels in the remainder of this work. So here a quick example to understand. Suppose we're working on speaker recognition. So our final downstream labels are Ys, the speaker IDs. We have the speech samples, and we have this speech-related feature Z that we're using its prediction as a pretext task. So we know we can infer Z and Y directly from X, but what we want to know here is how much we can infer Z directly from Y without knowing much about X. So how strong the dashed arrow that is represented here is. So this quantity is not trivial to compute. And in our first work that has been presented at the last interspeech, we actually introduced this independence criterion, this Hilbert-Schmidt, and it's not we introduced this, how to compute the Hilbert-Schmidt independence criterion on speech data. And it's a kernel-based independence testing so that we would only need similarity measures between speech samples and between the pseudo labels. I won't delve into the details of this calculation, but the main point is that you would go from an independence testing, which is the HSIC, to a conditional one through splitting through the downstream labels C, and we'd have this score of how much X and Z are independent given Y, conditionally on Y, and this score, as shown in the paper at interspeech, correlates well with the final downstream performance. So that's the starting point here. And in this work, the main idea is that in multitask self-supervised settings, we do not learn to predict a pretext task individually, like in the work that has been presented at interspeech, but we do predict a bunch of them simultaneously. Here you can see this schema that comes from the PACE Plus paper from Pasquale Ravanelli and collaborators. And you can see here through the workers that they do predict a group of pretext tasks simultaneously in order to get the base features, which are the speech embeddings of interest here. So if we can select individual pretext tasks, how do we do this multitasks, this group selection? And if we learn a group of tasks simultaneously, if we solve a group of tasks simultaneously, the question that raises pretty naturally is how do we weight them? How do we point the pretext tasks that will have the biggest loss during the self-supervised phase? So the problem can be resumed in this part. So the input is a group of individual pretext tasks, is a set of individual pretext tasks, so the Zs. And the objective is to define the best regrouping pretext task Z lambda, which is here an orthogonal concatenation of weighted pretext tasks, with the weights being the lambdas here from lambda I1 to lambda k. So those weights will correspond in the self-supervised phase to the losses corresponding to every pretext task. So if those weights correspond to a loss, they should respect a few constraints. The first one is pretty clear. They should be positive, because if when we're learning the representations, we do have negative losses, this would mean that we're trying to unlearn something, and then we're in a kind of adversarial learning setting, which is not the case or the scope of this paper. They shouldn't be too low. That's the second constraint, because that would mean that we're not learning a lot of things. If we have very low weights for our pretext tasks losses, that would mean that we're not learning here. So we to allow a fair comparison, we have a constant sum of these lambdas. They would sum to 1 in the remainder. And finally, the third constraint is a constraint that we would prefer. We would prefer, since we're talking about selection, we'd prefer a sparse weighting vector, so that we wouldn't learn all the pretext tasks, but the ones that we select, and the other ones would have a 0 weight, so that we wouldn't even need to compute them. So how do we enforce those 3 constraints? Actually, we will minimize the scoring function that has been defined in our interspeech paper, so the HSIC, according to lambdas, and those lambdas will be the output of a function of 3 parameters W, and the functions, the first function that we chose was the softmax functions, because it outputs positive values that sum to 1, which is the 2 first constraints. And in the second experiment, we would replace the softmax function with the sparse-max function, which is another function that outputs positive values summing to 1, but in a sparse vector with the zeros, eliminating thus a few pretext tasks. So the important thing here is that softmax and sparse-max are both differentiable, allowing for gradient descent optimization of the HSIC. So how do we validate this approach? We do first compute those weights in the first box above here. And then in the self-supervised training, we use those weights here as a weighting for the losses of the pretext tasks, along with the reconstruction target of the spectrogram. And then we take those representation and we see the final downstream performance. And we're expecting a better downstream performance than baselines methods to select pretext tasks. So which are the pretext tasks that are considered? We considered very quickly a bunch of them, mainly related to pitch. They are inspired mainly from the signal processing literature and the feature processing, the feature selection literature for speech tasks. And the data sets are presented here. So the ones used for pre-training, here common voice for speech, and the downstream tasks we're considering here, ASR, speaker recognition, and emotion recognition. Since we also held experiments on music, we do have a pre-training data set for music and 2 downstream tasks, which are solo instrument recognition and multi-instrument recognition. So you can see in this slide the first results. So you can see the loss here, which is a reconstruction of the MEL spectrogram, MFCC prediction, and the summed losses weighted with the lambdas here. And you can see that the models in the 3 considered downstream tasks, ASR, speaker recognition, emotion recognition, the performance are the best performance are the ones obtained with the softmax and the sparse-max weighting and selection, compared to the base plus paper and to say baseline selections actually inspired from the group feature selection literature, which are MRMR and RFE. So you can see here that the results are still not as good as the state-of-the-art methods. And we actually wanted to see how much we could maybe improve state-of-the-art methods going from powerful CPC tasks like the WAVE to WAVE 2.0 and retraining these models, adding a carefully selected and weighted pretext tasks like in the loss that is presented here. So we'd have the CPC loss plus a sum of weighted losses. And we do that on the 3 considered speech downstream tasks that are presented here. And we still here, and we can see here that the final line, which is our line, is better in the 3 ones and in the frozen and the fine-tuned setting, like frozen and fine-tuned corresponding to freezing or fine-tuning the self-supervised weights. So this was for speech. And to test the robustness of our technique, we actually extended to music. Actually, our technique is not really only relevant to speech or neither to audio. We can also do it on non-audio data, but we tested it on audio, on other audio data with music. And you can see here that on medley, solos, or open mic, we still have the best results with the softmax and sparse-max weighting and selection. So can we select those self-supervised pretext tasks optimally? Yes, we do that in a very efficient way using the conditional independence here. And we extended the work presented to interspeech to multitask, which is the work that actually is of interest. And this opens an efficient way for self-supervised learning pretext task exploration in the future. Thank you for your attention. I'll be open for any questions you may have afterwards.
Yeah, thanks, Salah, for the presentation. Let's move for the 4th paper we want to discuss for today, which is Delores, decorrelating latent space for low resources audio representation learning.
Yeah, hello, can you see my screen?
Yes.
Oh, yeah. Hi, everyone. I am Ashish, and I'm currently doing my master's from Indian Institute of Technology, Madras. And this is the work, which is Delores, which is decorrelating latent spaces for low resource audio representation learning. It's a combined work between IIT Madras and various analytics. And the main motivation regarding the Dolores architecture is to create general purpose audio systems for audio classification. So in this paper, we have introduced Dolores, and we are using Barlow loss, which is basically a very important loss function, which is being used in computer vision. And we have tried to generalize our system across speech and non-speech tasks, like speaker verification, speaker identification, keyword spotting, and some non-speech tasks like bird sound detection, musical instrument. So we have collected 9 such downstream tasks based on prior SOTAs, and we have tried to merge all the results accordingly. And our goal is to create a robust and simple end-to-end network for journal audio classification. And we also want to push the research for self-supervised learning towards low resource self-supervised pre-training. So here are the data sets that we are using for the downstream as well as for the upstream tasks. So if you see the table 1, it shows the 9 downstream tasks that we are kind of evaluating our system on. So you can find speaker identification, emotion recognition, keyword recognition, song detection, bird song detection, language identification, and musical instrument identification with the respective statistics. And the table 2 represents the data set that we are using for the pre-training setup. So as you can see, we are using audio set and we are taking 0.2 million of it. And then there is FSD 50K. We are taking 50,000 samples from it. So now I will try to explain the approach that we are following for our general purpose audio system, which is Dolores. So basically what we try to do is we have a WAV file and we try to convert it into log-mel spectrograms. And then we use data augmentation techniques like mix-up and random resize crop, which were famous in computer vision. And we have tried to adopt it for audio and speech domain also. So these augmentation techniques are very important. And what we try to do is we try to create 2 sets of batches based on these augmentation techniques. And we pass these 2 sets of batches to the same encoder. And after that, we get our feature embeddings. These feature embeddings are projected into higher dimension with linear layers. And these projected batches are then used to calculate cross covariances or cross correlations. And the idea about the loss function is basically to try to have cross correlation between two augmented batches for the same audios to be as close as 1, and the rest of the cross correlation to be as close as 0. So basically our target cross correlation matrix would be an identity matrix, and furthermore about the loss would be explained in the future slides. So after pre-training our encoder using this strategy, now we have to evaluate it. And the way we are trying to evaluate our encoder is using 2 setups. One we call as linear evaluation setup, and other one is called as transfer learning setup. I will try to explain both the setups in the future slides. And then we use both of these setups to evaluate on these 9 different type of downstream tasks. And we get the scores and we try to compare on the other state-of-the-art architectures which are doing the same thing. So here is the pre-training objective. So the second equation basically represents the cross correlation calculation. So the whole idea is it's basically the same thing. The way we compute a basic cross correlation, we try to make it 0 mean and then unit variance. And the same thing happens here. We use batch norm to make it 0 mean. And then after that, we standardize it using dividing it into square of the standard deviation. And then we have 2 terms. One is called invariance term and another one is called redundancy reduction term. Invariance term basically represent that the cross correlation between the 2 augmentations of the same sample should be very high, very close to 1. And the second is redundancy reduction term, which basically represent that other cross correlations should be as close as 0. And the lambda is basically a hyperparameter that try to kind of take the importance of redundancy reduction term in the overall computation of the loss. We have tried different values and we found that for our speech setup, the lambda equals to 0.001 works very well. Now I will try to explain the augmentation strategies that we are using, because we are using Barlow loss basically depends on cross correlation, and it's very important to do proper type of augmentations. So the first augmentation strategy is called mix-up. The idea of mix-up is we take a log-mel spectrogram And then we have our Q, which is basically an accumulation of past log-mel spectrograms seen by the model. And we take a random sample out of it. Because it's a log scale, we try to convert it into a linear scale by doing an exponent. And then we have our weights, which are called alpha. And then based on these weights, we try to combine all these two. And then we again convert it into log scale. And this is how the mix-up is done. Usually the Q is very large. We have made it to 2048 so that it doesn't depend on batch size. The second is the random resize crop. And the idea of random resize crop is basically to crop a part of a log-mel spectrogram. And to do it properly, we also use a virtual crop area. And the rest of the detail can also be found in the paper. Now the result. So we have used two types of setups to calculate the results. One is linear evaluation protocol. The idea behind linear evaluation protocol is to take the pre-trained encoder and then try to freeze all the layers of the pre-trained encoder, and then basically use a single linear layer to train it for 100 epochs. So while training, all the other layers would be freeze for the encoder. So as you can see, the other state of the arts, we have mentioned all the scores, and we, out of 9 downstream tasks, we are achieving the best scores in the 5 downstream tasks. Then the second setup is transfer learning setup. Basically, we take the pre-trained encoder, we don't freeze the layers, and then we allow it to train for 100 epochs. And similarly, as you can see that out of 9 downstream tasks, we are having best scores in the 4. Then there are some plots which tells us about the setups that we are trying to do. So the first plot, if you see, is basically a representation of the number of parameters that different type of architectures have while doing this type of problem. And then it's the y-axis shows the accuracy on the voxel, which is a speaker identification task. So you can clearly see that our architecture, which is Dolores, is having 5.3 million parameters, which is comparatively less than all the architectures present in it. The state-of-the-art architecture in the voxel, which is SSAST, has 87 million parameters, and we are competitive with the results. The second plot here shows that how our pre-training strategy is helping. So basically what we have tried to done is, we have taken the encoder, we have transferred the weights from the pre-trained encoder, and then we have used the transfer learning setup, and we have compared it with randomly initialized encoder, and basically we kind of run both the encoders for 100 epochs. For this graph, we have only shown it for the first 11 epochs, and we have averaged out the accuracies for all the 9 downstream tasks. So you can see there are 2 curves, like one is the orange curve, another one is the blue curve. And we can see that the blue curve, which is present Dolores, is starting from a better initialization. And for at least for 11 epochs in the graph that we can see, it's always above than the orange curve. So now I would like to present some of our future work that we are doing in this same domain. So basically, while doing pre-training, while solving this problem, we have found that the pre-training dataset that usually being used by other state-of-the-art, which is audio set, is of 20 million. But because the way the audio set is being downloaded, it tries to crop some part of the video of the YouTube and then try to download the WAV files. Some of the downloading hitting rate is basically 30%. So we are not able to download the whole data set itself. So what we have tried to introduce is, we have tried to introduce a LABE benchmark, which we call low resource audio processing evaluation. And what we have tried to do is, we have tried to create a CSV file basically, which is label balanced. And so that, and it contains 2 lakh audio samples or 0.2 million audio samples from the audio set. So that now other small research lab can easily utilize this file and CSV file for their other pre-training process. And also we are providing all the downstream splits that we are using, so that people can have consistent results. Second is we have tried to increase our domain of evaluation. We were evaluating on 9 downstream tasks. So now we have added more evaluation tasks like acoustic scenes. In acoustic scenes, we have TOT Urban and Urban Sound 8K. We have tried to integrate those also. And we have tried to develop a newer architecture which depends on student-teacher network and it uses Barlow loss as an intermediate layer loss, and it combines it with the contrastive loss. So by using this newer architecture, we are able to achieve better results in we are able to achieve state-of-the-art results in 7 downstream tasks out of 11. So that is the second thing that we are doing. And the third thing is, because of the time constraint, we were not able to do a lot of other evaluation studies, which are very important in these type of tasks, like what type of encoder we should use, what type of normalization you should do, and we should also test layer probing. Basically, we should take the features from each of the layer and try to evaluate them and see which layer is giving better performance for what type of task. So we have tried to also do these type of things, and have tried to put all these results. So thank you, and it was a great opportunity to talk with you. So yeah, if there are any other question, I can take it. Yeah.
Yeah, thanks, Ashish, and thank you so much for all the 4 papers and the speakers. I think we have several minutes to talk about our questions. I already seen there are several discussions in the chat, so maybe we can start from several questions not answered at the moment. Maybe I saw Anuj, you have a questions for the pretext text selection paper, so maybe you can share your question with us, and then we can have a speaker to answer.
I can actually try to answer the question from Anush since I can read it. Can you hear me?
Yeah, so yeah, in that case, maybe let me read the questions. So the question is, the conditional independence criterion was used to select weight and in an appropriate set of pretext text. Is there any easy way to extend this idea to select a subset of the training set for each pretext task as well? For example, select the best possible training set for each task. This is related to the general idea of data subset selection for training machine learning models that can lead to a better performance with less data.
Thank you, Anuj, for the question first. I'm sad to say that I think the answer is negative. The method that we present here, when I say about X and Y, I'm talking about the downstream data set. So the main idea here is that we're selecting pretext tasks as a function of the downstream task we want to solve at the end. And we're very interested in our team in this question of data selection, and actually the literature on that has been pretty interesting as well. I can point you to the robust WEF2WEC 2.0 paper from Weining Su and collaborators, which shows actually the importance of the data set that is used in the pre-training concerning the final results. But the conditional dependence technique, I've tried to think about a way to use it for data set selection, for pre-training data set selection. But since it doesn't involve the pre-training data set, I'm sad the theoretical works that have been done by Jason Lianal on proving the utility of the conditional dependence fall short here for this question. But yeah, the question is very interesting anyway.
Yeah, thanks a lot for the
and just to answer the second question from Wei Tsung Kao, I can read it if you want. So the question is, have you tried to extend the proposed method to select the existing self-supervised learning methods? Yes, we've been actually thinking about that in the lab, and maybe it will concern next works. But the problem with those tasks is that they would require different kernels. I mean, when you're talking about tasks that are only consist in predicting a pseudo label, and the pseudo label, the label is clear, and you can like perform similarity measures, but in the label space. But if you're talking about contrastive predicting, the labels are pretty much higher, so you'd have to come up with new sets of similarity measures, and this is possible, but we haven't yet delved into this.
Yeah, thanks for Salah for answering both questions. And I think the next question is for Ashish, and the last paper from Yonggang. The Yonggang want to interested like, do you fine tune the entire model on Voxlab?
So basically we have done both the things. So basically we tried to evaluate the voxelf for the while training the whole model also, and we have also freeze the encoder and itself and just tried to train the linear layer. So the answer is we have done both the things, and yes, yeah.
May I ask follow up, like for fine tuning the voxelf, like how long it takes?
Yeah, so what we have done is we have only used voxelf v1, and so it takes around 1 day to complete it in one GPU. Yeah,
I see. Yeah, thanks for the answer. I saw there are some questions for the first paper, and they already have some discussions. Maybe we can also talk about that as well for visibility for the entire audience. And maybe we can start from, I know Huck, you have a question for Haibing regarding like a number of parameters for affecting the performance. Maybe you can summarize the question and we have Haibing to respond to the questions.
Yeah, thank you, Daniel. I think that question has been answered. Yeah, I'm good. Appreciate it.
Yeah, but I feel like if you can share your
Oh.
questions, and I think for visibility of the audience, that would be great.
Sure. Thank you. So mostly in terms of model robustness, there's a conversation between whether a larger model have a better adversarial robustness or not. So I'm just wondering, for different size of SSL model, does the size of parameter affect the final performance against this adversarial noise? Yeah.
Yeah, Haibing, would you like to give us some insights?
Okay, thanks for the question. Very good question. And actually, in this work, we did some experiments on wave vector and Hilbert. They actually have the same structure and the same parameters. We didn't try other structures. And I think in the future work, I will consider Huck's comment in my future work and to investigate whether a larger model will attain more robustness, more adversarial robustness. Yeah, thanks for Huck's comments.
Yeah, thanks for the response. And I'm also thinking this is a very interesting direction. And in addition to that, exploring like different type of pre-training tasks and related to robustness probably is also something the community can benefit from such analysis. Yeah, and I think I also see a question from Wenqing. I think it's also get answered later, but I think it's also good for the audience to have some discussion around that. So I can also repeat again the question and have Wei Chen to share more insights. So basically the question is, can you explain more like why MIA is an important task? What kind of threats can there be if we found a specific speech sample is used to train the SSL model? Wei Chen, would you like to give us some insight?
Okay, so could you hear me?
Yes.
Okay, so about this question, we can first consider a future scenario here. Assume that there's a self-supervised speech model that is pre-trained on a data set that contains of recordings of online clinic. Then if an adversary can infer whether a speaker contains in the pre-training corpus, then it is equal to knowing that the current speaker, does the current speaker goes to the online clinic or not. So it is basically, it is a kind of serious privacy issue. And moreover, the membership inverse attack is often considered as the easiest privacy attack. And if a model is vulnerable to membership inverse attack, then it is more likely to suffer from the other type of privacy attack. For example, the model inversion attack, the property inversion attack, or the model extraction attack. Thus, the membership inverse attack can be a good entry point of analyzing the potential privacy risks of the self-supervised speech models.
Yeah, thanks Wei Chen for the insights. I think we have learned a lot from the 4 different works. So, and thanks so much for speakers, the time out of your regular working hours, but you still present a very great summary of your innovation. So thank you much. I think we are at the end of this session. So the next, we will take some breaks and we'll come back at 1:20 Eastern time and with an invited talk from Weining. So I will see you in maybe 22 minutes.